Anyone's ready?
I guess. Solo thing.
Okay, let's get started. Let me have your attention, please. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is really one of our own. It is Mr. Ron Green. Ron received a BS in Engineering Physics from UT in 1970, and then a Master's in Engineering Administration in 1978. While he was between 70 and 78, he worked in the Centrifuge program at the K-25 facility in Oak Ridge. In the mid-70s, he became an officer at U.S. Nuclear Corporation, and then in the late 70s, he joined the Clinch River Breeder Reactor Project. He was with them until in 1982, he joined Daniel Construction Company, which at that time was the largest construction company in the world. He supervised the construction of 10 power plants, I presume mostly nuclear power plants.
Nuclears and 50 other non-nuclear.
He's also had a diverse career. He worked for Duke Energy, for Shell Oil, for Florida Power and Light, and for the Hanford plant in Washington, which is a DOE facility similar to Y-12. And then in the year 2003, he became the Chief Executive Officer for the U.S. Enrichment Corporation. That's the position he has today. He is the winner of the Nathan W. Daugherty Award, which is the highest award that our college presents. We present it each year. He won it in 1993. And he's been a member of the College Advisory Board since its inception in the mid-'80s. One other piece of information, he played baseball for UT, okay, back when he was an undergraduate. And so, ladies and gentlemen, please welcome Mr. Ron Green.
Thank you. It's a pleasure to be here. And to our broader audience as well. I emphasize that 1970 because I want you to understand how much younger I am than Lee. Made sure that he said that. What we're going to do today is talk about uranium enrichment, what we're doing as USEC with the centrifuge, the gas centrifuge that was developed over a number of decades by the U.S. Department of Energy and its predecessor organizations, and now it's being deployed commercially, which that's the program I'm in charge of. I think what we really want to do to talk about today is that we intend to demonstrate the technology, to bring it off the shelf, if you will, where it's been for 20 years, and build a commercial plant, operate that plant. I'll try to convince you that it's based on a proven technology. I think that's not too hard to do. And when it's deployed, it'll be the world's most efficient uranium enrichment technology, and I'll tell you why that is and how that works. I believe an important thing to know, though, is that it benefits not only the USEC shareholder, whom I represent or work for, it benefits the industry at large. I believe more strongly than I have at any time in the past that we're looking at a nuclear renaissance in this nation. And you have to have a strong and secure fuel cycle to have a strong nuclear option. So it's important from all those points of view. A little history lesson here, if you don't mind. Starting in 1960 in Oak Ridge, out at what's now ETTP, or what was K-25 site, the predecessor to the U.S. Department of Energy started seeking a large and fast centrifuge machine. Those of you who know the history of the Manhattan Project know that there were several ways of enriching uranium to make the first weapon. Centrifuge was considered, but it was considered not ready for commercialization at that time, but it was worked on subsequent to that. Gaseous diffusion was ultimately selected, and that's how the first weapons material was made at the K-25 plant, which was built as a part of the Manhattan Project. And then later on, plants were built in Paducah and Portsmouth, or Piketon, Ohio, as you may choose to call it. And that's kind of where we were at this time frame. Diffusion is a wonderful technology, but it requires an enormous amount of electricity. Centrifugation allows one to do the same amount of separative work for only 5% of the electric energy. So it's a net savings from that point of view. A total of about $4.3 to $4.4 billion was spent by the U.S. Department of Energy during the time from 1960 to 1985. What happened during the time frame of the mid-'80s was that 3 Mile Island's impacts had been worked its way through the industry, and the number of projected nuclear units had gone from being a healthy curve to a flat or even declining curve, and it wasn't felt that we needed to complete the GCEP, or Gas Centrifuge Enrichment Plant at Piketon. It was partially built. I was involved in that, but it was terminated in the 80s when the realization hit that we weren't going to need as much enrichment capacity as already existed with the diffusion plants. There's another phase of the project that's shown here called the Advanced Gas Centrifuge Program, and during that time in the early 80s and ending in 1985, the Department of Energy was seeking a bigger, faster centrifuge machine, and I'll go into a few minutes why that's important, why that's worth doing. We actually demonstrated in those days separative performance on a per-machine basis that exceeds the targets that I'm working to today. So we've already shown that this can be done. And that's why I talk about proven technology. We were over 300 separative work units per machine back in that time frame. This is an interior shot of the Piketon facility. If you haven't been in there, it's impressive in its size. Between the two process buildings that were built in the late 70s, early 80s, and the large building that was put in place to put together and take apart centrifuge machines called the R&A Recycle Assembly Building, there's a total of 20 football fields under roof. I mean, this is a big place. And a number of machines were installed, 1,300 machines were installed at Piketon. They didn't all operate for a long period of time, but some of them did. And the target per machine was a modest, if you will, 200 swoop per machine per year. So that's a little bit of the history of how we got where we are. Let me talk a bit about the centrifuge machine itself and point out some of the salient features here. The centrifuge really it's complex in some aspects, but the theory of it's pretty simple. There's a right circular cylinder called a rotor tube that spins rapidly inside of an evacuated casing. Under vacuum, it's hard to spin something real fast if it's not under vacuum. It's too much drag, if you will. What one does, introduce uranium hexafluoride gas, which you probably know is not a gas at room temperature. It has to be elevated a little bit in temperature to stay gaseous. Introduce that near the center, in a thing called post, near the center of the machine, and the centrifugal force of the rotor and the gas spinning together will tend to take the U-238 isotope closer to the wall and downward, and the 235 isotope being lighter and feeling less centrifugal force because of the difference in weight toward more away from the wall and upward. That situation is exacerbated, if you will, by the intentional application of a thermal gradient. And as you can see from the arrows indicating the gas stream, the the heavier material tends to go toward the wall and down. The lighter material tends to go away from the wall and up. And it allows the opportunity to pull depleted material out of the so-called waste scoop that's inserted into the gas stream. And it lets you pull product material out of the enriched scoop. And that in essence is the machine. The machine, of course, doesn't do all the work in just one machine. There will be in the commercial plant, there'll be thousands of these machines, and they'll be organized in what's called stages. And this little diagram here is intended to indicate the relationship of the machine and all the things that it has to have to the rest of the plant. Actually, it has to have a vacuum system, cooling system, various sensors, probes to tell you the condition of the rotor tube, and the feed product and tails lines are aluminum tubes, if you will, that through which the UF6 travels. And the output from this machine would become the feed into the next stage machine, and so forth on down the line. The tails would go down the line in what's called a stripping cycle, so that at the end of the stages, one would have reactor grade enriched material, which these days is the most popular enrichment level these days for today's reactors is about 4.95%. We know that in advanced machines, advanced reactors, it's going to be a little higher than that. So as we're licensing this technology for commercial use, we're licensing it to be able to produce up to 10%, just in case an advanced reactor design requires something higher than what we're producing today. The other thing that's interesting about this line is everything to the left of the line is being done in Oak Ridge. Everything to the right of the line is being done in Ohio at the existing diffusion plant site, which is where the GSEP facility was originally built. I have today about 180 people in Oak Ridge doing the design, development, testing of the individual centrifuge machines. We're preparing later this year to send machines to Piketon to be installed in a cascade format in a test bed that's called the lead cascade, or the American Centrifuge Demonstration Facility. That'll be done late this year. We're testing individual machines now and cascaded machines later in the year. The theory of separative performance of a centrifuge is indicated by this simplified Dirac expression, and I really want you to focus on just a few things here. Number one, that is not diameter. That's an expression of self-diffusion. Please note that this expression tells us that a big tall centrifuge is better than a short centrifuge because it's proportional to the separative power is proportional to the length. So the longer, the better. It also tells you that it's proportional to the fourth power velocity. So it's to your benefit to make your rotor spin real fast. And that's what we build. We build a large, fast-spinning centrifuge machine. These little things at the bottom are indicative of our machine is over 40 feet long. The European machine that competes with us to some degree is about a third of that length. The Russian machine, which is called a Zippy machine, named after Dr. Gernot Zippy, who actually invented gas centrifuge technology when he was a prisoner of war, and then kept by the Russians from 1946 until we brought him to the United States to work with Dr. Beams at the University of Virginia. This is a Zippy machine. It's only a little less than 3 feet tall. So were you to go in a uranium enrichment plant in Russia that's running on centrifuge, you'll see bank after bank after bank of these little bitty machines. You go in Europe, whether it's in Britain, the Netherlands, or Germany, you'll see a machine that looks like this. Go in our plant, you'll see a machine that looks like that. And that relationship there tells you that, well, one other thing it tells you, I think. It tells you that velocity is important. It tells you length is important. You don't see diameter in there anywhere, so diameter is not important. And, of course, you'd like to lower the temperature, but you're limited by the need to keep the UF6 in a gaseous phase. So you really can't do much with that. You can't lower the temperature significantly. You keep it at a temperature just enough to keep it in the gaseous phase, but you can't go below that because then you don't have UF6 gas anymore. It would plate out as a solid. Now, why do I believe that we're even going to do a better job today than what we did 20 years ago? Well, there's several reasons for that. Better materials. We realized in the 80s that a carbon composite rotor would be a wonderful thing to have, because the velocity at which you can spin the rotor is the relationship between tensile strength divided by density. And so carbon fibers has enormous tensile strength and is not very dense. And so it's a good rotor material. It's much better than maraging steel or other materials that are used around the world that you may have heard something about. That material, when I worked on this earlier in my career, the carbon fiber material was an exotic material. There wasn't much of it. There wasn't much being made. And it was a very short commodity and very, very expensive, prohibitively expensive. Now, not to be simplistic about it, graphite composites are in bicycles now, mountain bikes, tennis rackets, golf clubs. It's not an exotic material anymore. It's come down in price, so that's a good thing for us. Manufacturing techniques exist today, as you would understand, that didn't exist in those days. I mean, we have multi-axis numerical control machine tools that cut to and polish and grind to very, very tight tolerances that weren't possible in the 70s and even the 80s. We have more computing power in this little PC over here than we had in our entire K1600 test laboratory in the 80s. I mean, that's important. And control systems have been greatly improved. So we have better software, better analytical capabilities, better materials, and all these things lead me to believe we're going to make an even better machine than the ones that existed before. When you're setting out to design something like a centrifuge, you kind of think of it like an airplane, if you will. It has a design envelope that it's supposed to operate in. And these are the parameters that sort of define that design envelope. And the maximum values ever demonstrated by the Department of Energy program are shown over here on the right-hand side. And as you can see, whether it is in the area of speed, stress, the length of the machine, how much gas inventory, the flow rates, the assay that's being produced, all those things together define separative performance. And we're not taking any of those really close to the maximum value on the design envelope, because as in an airplane, if your airplane is designed to be able to withstand so many G-forces and you take it to double that, the wings tend to come off. And you don't want that sort of thing to happen. So we're very conservative in the selection of these design values, and we don't take any of them near their not theoretical maximum, but they're already proven values in the Department of Energy program. Our deployment is organized into three pieces. The centrifuge testing piece, which is being done right now, Oak Ridge. This is Oak Ridge. This is Piketon. And the commercial plant obviously is also in Piketon. So this work right here is being done right now. I'll tell you a little more about exactly what we're doing. But we're building the first centrifuges that have been built in 20 years, and we're testing it right now in Oak Ridge, the individual machines. Then we're going to send a number of machines, up to 240 machines, to Piketon to populate what's called the lead cascade, or the demonstration facility. And that's where we'll pipe the machines up in cascade format with the product out of one being the feed into the next and so forth. And we'll demonstrate there that we can produce the desired customer assays. You tell us you want 4.95%, that's what we're going to make. Whatever the customer tells us he wants, we'll demonstrate how to make that assay. When we're satisfied with that, We then deploy thousands of centrifuge machines in what's called a commercial plant, and that commercial plant will cost up to $1.5 billion, and will employ up to 500 people in Piketon. And you got to remember that even though USEC, which is short for United States Enrichment Corporation, used to be an arm of the U.S. government, is not anymore. 6 years ago, it became a publicly traded company on the New York Stock Exchange, and we're doing this for our shareholders. It happens to have a benefit to the nation, it happens to have a benefit to the nuclear industry and the option, but this is a play for our shareholders. We're doing this to earn a return for our shareholders and to wean ourselves eventually from the very energy-intensive diffusion plant. On an average day, let's just take last week. Last week, the Paducah diffusion plant was consuming on a 724 basis almost 1,400 megawatts. On a different set of conditions, it'll be consuming 1,600 megawatts. That's a lot of power. It's the biggest industrial power utilizer in the nation. It's the biggest customer TVA has. And if you know anything about the wholesale electric business, you'll know that commodity prices have been on a rapid increase here lately. And we feel like that eventual exposure to the commodity price world through the wholesale electric business by buying that much power is a risk for us. We're trying to control our risk profile by doing the same amount of separative work using only 5% of the power. That's what really gets Centrifuge started. I mean, that's the why to why we're doing this. We think the program's laid out intelligently, and that commercial plant is intended to be operating by the end of the decade at its full 3.5 million SWU performance level. Looking at the schedule, you'll see that. You'll see a couple things. Number one, you'll see the plant operating by the end of the decade. And number two, you'll see that the years 05 and 06 have an awful lot of activity going on in them. You know, you begin testing, you begin manufacturing, you start operating the lead cascade, you're getting performance data, and by the way, you're going to the financial markets to secure funding for $1.5 billion. That's a busy time, and we're right in the middle of a busy time right now. But I think the eventual result will be fantastic. Now, USEC has a third of the world's business for enriched material, enriched uranium. Last year we delivered about 11 million SWU. That tells you that the world market is 3 times that, or about 33 or so million SWU. That world market is growing a bit because reactors are underway in Mexico, India, Scandinavia is again building. China is coming on with 30 units. So the world SWU market is a growth business, not a stagnant business. I believe we'll have a nuclear renaissance in this country before very long, particularly since Bush got a second term. I think that's going to bode well for the option. So in order for us to satisfy the needs going forward, we probably cannot afford to stop at 3.5 million SWU. I mean, we deliver 11, and I'd like to shut off the diffusion plant. Well, I've got to build more centrifuge, and I can add about 1 million a year at the rates that we're going to be manufacturing commercial machining. So this thing is big. It could get very, very big, is my point. And we have a very carefully laid out program. Let me give you a little more detail on what we're doing out in Oak Ridge. At a place called the CTC, or Centrifuge Technology Center, that sits adjacent to the Boeing building, if any of you are familiar with Oak Ridge. Boeing built a plant in the 70s to make centrifuges for the DOE program. We're leasing one of those buildings. It's our centrifuge technology. It's full of machine tools, rotor winding equipment. We make the rotating parts and we test them there. Then we have another facility out inside the loop of the old K-25 Manhattan Project plant. Sits a tall building called K-1600. It's there that we test the full-scale machine. We balance the rotors, and we put them on gas to check their separative performance. Those are the 2 facilities we have in Oak Ridge. And by the way, we're in the middle of doing this right now. I'm out there this morning. We're right in the middle of our testing phase. We also have some relationships that are important. As I told you, USEC is formerly a part of the Department of Energy back in 93 to 98. It's now a publicly traded company. It's owned by our shareholders. We have a cooperative research and development agreement with UT Battelle, as you know, operates ORNL. And then we have an agreement that was put in place in 2002 with the U.S. Department of Energy, which gives us the right to lease facilities, gives us the right to use the technology, and we're seeking a license from the Nuclear Regulatory Commission. So those are the relationships that we have in play. We'll have a fuel cycle license from NRC for both the lead cascade and the commercial plant. Then in Piketon, at what's called the demonstration facility or the lead cascade, your choice. We're going to send machines up there. We're going to pipe them up in the cascade format and prove that we can make customers' level of assays that are desired by the customers. And the difference in this and diffusion technology goes on and on. It's not just the electricity consumption, though. This technology, unlike diffusion, is very modular. Let's say that we get a new customer and he wants to buy 300,000 SWU per year. I can add just that much capacity in the plant, just to satisfy it on a per contract basis. Diffusion plants don't work that way. They're either on or they're off. When they're on, they're consuming an enormous amount of power. When they're off, they're completely off. You don't have modular opportunity in a diffusion plant. That's another advantage of Centrifuge technology, which is another reason why we're doing this. And that's a little picture of the machines that were installed in the early 80s. I know the colors look a little funny. We do not paint our machines pink. They just look that way under this particular light. And as I mentioned, they are over 40 feet tall. And what we're doing right now is we're removing these machines, making space to put in our lead cascade at the Piketon plant.
They were 40 feet tall back in the 80s?
Yes. Some were even taller in the so-called AGC, or Advanced Gas Centrifuge program. That's a summary of what we're doing. I'd be happy to take questions if you have them. Okay. Yes, sir.
Why did this facility get shut down? What makes these obsolete?
Well, it was just a supply and demand situation. You mean these machines?
Yes.
Oh, we've greatly improved parts of the machine. I wish I could go into the details on that, but without a DOEQ clearance and a secured facility, we can't talk about those improvements.
Let me rephrase this question in a different way. I can remember back when we had two technologies. We had centrifuge technology and we had Atlas, atomic, vapor, laser, isotope separation.
That's correct.
They were competing.
That's correct.
And at that time, the decision was made to go with Atlas and to abandon centrifuge.
Yeah, to eventually go with Atlas is correct. But at the time the decision was made, we didn't need any more enrichment capacity. We already had enough.
To eventually go with Atlas.
Eventually they were going to go with Atlas.
Well, so we stayed with Atlas all these years, and then here again, the last few years, they decided, hey, Atlas is not the way to go. Let's go back and do centrifuge.
Atlas was not anywhere near as ready for commercial deployment as centrifuge is.
Okay.
That's the reason we USEC dropped Atlas.
Okay.
And went with centrifuge. We're the ones that made that decision, not the government.
If they were going to shut some down, why did they shut the centrifuges down and not the diffusions down if they have such...
Well, the diffusions were already built. They were already invested in, and power plants had been built just for the purpose of supplying the electricity to all the diffusion plants. That infrastructure was all in place, and this would have cost a lot of money to build. This was
never completed.
You're looking at how much was completed right there. There are 2 process buildings, an RA building, and 1,300 centrifuges. Yes, sir.
What exactly will happen to Paducah once you get the facility online?
Over time, Paducah will quit operating.
Does the U.S. Enrichment Corporation cover the costs for shutting down Paducah, or is that set with the government?
Yeah, when you have it's not unlike, it's like any other nuclear facility. You have an NRC license that tells you what you have to do during D&D. Yes, and we have sufficient financial vehicles in place to ensure that. Yes, and the same thing will be true for the centrifuge plant. I have a D&D plan for that. I hope it doesn't happen for 50 years, but when it does, we'll have the financing in place to take care of that.
Martin, you had a question.
Yes, sir.
Would you turn back to the slide that had the equation for slews? If I want to look at that a little different way, and if I substitute R omega for B, now I have the slews proportional to the horsepower of RPM and the third power of the radius. So for a constant RPM, if I make the machine larger, as long as it doesn't tear itself apart, then I should get a higher output.
No, sir. It doesn't work that way.
Well, why not? What happened?
The radius and the diameter of the machine doesn't play into this equation.
Well, the way you have it, that's fine, but I mean, you're looking at the velocity of your rotor.
Yeah.
If I want to look at the RPM...
Well, in a practical world, making a large diameter rotor is not a good thing to do. Because it'll tear itself apart. I mean, in theory, okay, but in the real world, it doesn't work. It won't work. You got to have a long, fairly skinny rotor to make it work.
If you had a stronger material, then you could increase speed.
If you can give me a stronger material than carbon composite, I'd love to talk to you.
It's V that affects the strength of the materials. Especially the material is affected by V.
That's correct.
What's the connection between this and what whoever wants to build a plant in Louisiana? That's Duke or I forget who's in
Well, Duke, Exelon, and Entergy are buying output. They're not partners in the plant. That's the European technology that I showed. That's this one right here, the blue one. That's the green
built in Louisiana?
Yeah, well, they didn't build in Louisiana. Now they're in New Mexico.
Oh, I see. Okay.
Yes, sir.
How do you compare your efficiencies in St. Grade with the European and the original Russian?
Oh, yes.
In such a manner to assure in the future that we're going to be the lead organization in export of enriched materials to the rest of the world.
But we already
need that for economic linkage.
USEC already supplies a third of the world. We have 60% of the Japanese market, so we're already in that mode. Yes, and we're going with our centrifuge because it's many times. I can't go into how many times more powerful, but it's several times more powerful than a European machine.
Peter.
Ron, Cascade looks like a serious system to me. So reliability is important, right?
Yes, it is.
Because if one centrifuge goes, the whole cascade...
No, they don't. There's isolation valves.
I see.
But the most important valve on the centrifuge machine is the isolation valve. Sometimes the one machine, it's isolated. So we guard against that.
Okay, second question. I have trouble balancing my washing machine at home. It's spinning. I don't know if you can say anything about this, but...
I can't talk speeds and thicknesses. Sorry, it's not possible.
Okay.
But it's we've already done it.
Okay.
With the 1.5 billion that you're going after, how's that going to be? Is that going to be stock?
It'll be a variety of financing vehicles that have yet to be defined fully. But there'll be some equity and some debt component. There'll be as much leverage as we can apply to a structured financing. That'll depend on the markets at that time. You know, what do the markets look like in late 06? Half the cost is in the machines themselves, half the cost is in the rest of the plant, so-called balance of plant, half and half. And I'll have a better number when I've built a lot more centrifuge machines.
Colin?
What is it that stops the Europeans from doing what you're now doing?
I know, but I can't talk about it. I'm sorry.
I didn't mean technically, but is it patent protection? Is it knowledge? Is it people?
They're satisfied with their machine. It gives them performance that they're happy with. We're not satisfied, but they are. Their machine doesn't go as fast as our machine. It's not as tall. So therefore, it doesn't put out the separate performance. But they like it because it's highly reliable.
Thank you.
And I'm not trying to speak for them, but I'm just giving you what I believe their opinion would be. We want to take a different tack. We want the big, fast machine. It's sort of maybe it's an American thing. I don't know.
Older publications of 20 years ago said that the centrifuge consumed about 10% of the power of the gas infusion.
5%.
Oh, no, that's your machine.
Yeah. Oh, I can't
I'm
speak
thinking
to,
older literature said 10, so yours.
well, the smaller, yeah, you know, the little bitty, if you put a bank of, you know, 400,000 little bitty machines, I'm not sure what the power take would be, but it wouldn't be as efficient as ours. And Europe is in the middle, if you will.
As many of you know, this presentation is being webcast, and we do have the capability to accept questions from our cyber audience. And I have a question here. This question comes from Dr. John Church at the Savannah River site, and he's talking about, this is just comment directed to Ron. I may have missed it, but although there are demonstrations of various parts of the cycle, there seems to be no semi-work scale-up as part of your schedule. Is that because the theory and simulation are so well developed and reliable that such semi-works are not needed?
That's the, we have some very powerful analytical and simulation tools, the details of which are all classified. But frankly, we've modeled every piece of this with our simulation tools. We've modeled everything about the plant. But keep in mind that a big, fast centrifuge was demonstrated adequately 20 years ago.
Okay.
And we're very comfortable with that.
Okay.
And we know we're making better materials and better machine parts now because we've got better tools. So it just isn't. We do a lot of that, but it isn't truly necessary, as he indicated.
Martin?
Why do you have your operation divided between two sites? Why isn't it all at Oak Ridge or all at Tyson?
No, it's not. It has nothing to do with politics. Lee, I think everything's politics. It has to do with the center of centrifuge knowledge from 1960 to 1985 was Oak Ridge. That's where the people that we've hired live. That is, I'm 57 years old. I'm one of the younger guys in the centrifuge program, okay, from the old program. That's where the people are. And we're very comfortable doing our technology and development and design where the center of knowledge is. We've gone and gotten a lot of people from the old program. They live in Oak Ridge or surrounding parts. The reason we go in Ohio is because there's existing process buildings already paid for and already there that we can put these things in. We don't have to, we can avoid an enormous amount, hundreds of millions of dollars of expense by leasing buildings that already exist. That's the reason. Those are the two reasons. Politics is an assist, but it's not the reason.
I have a related question. There are also big, huge buildings at Paducah. Why did the government, in all its wisdom, choose Ohio site?
Government didn't choose.
Or
we chose.
Okay.
We chose. We did a careful site selection that had.
They don't know what happened, what the decision was. You need to tell them that.
Well, we did a careful site selection. The agreement we have with the Department of Energy in 2002 is that we'll put the centrifuge technology at one of the two diffusion plant locations. We get to choose. So we went at a contest between the state of Kentucky and the state of Ohio. Who wants this plant the most? And they developed incentive packages and tax abatements and job creation tax credits and other things of that nature, and Ohio won the contest. That decision was made last year.
Okay.
But we were bound to put it at one of the two places.
Right.
That was the agreement.
Yes.
Just wondering, just from other applications point of view, has this technology been applied to other aspects of traditional armament?
You wouldn't believe how often I get that question. And yes, it's used in some medical. The technology that was developed in Oak Ridge has been used in some very sophisticated separation work associated with vaccines and medical uses. There's also an application potential. I'm sorry, I can't talk about that. But there are other applications.
That was me, more specifically on engineering. Well, recently, NSF invested in building two large centrifuges at Davis and RPR. Look at earthquake engineering. Has anybody looked at that prospect? Those are traditional centrifuges.
I don't know about that. You're telling me something I don't know. I appreciate an email if you can tell me more about it. We did put them on shaker tables back in the old days. We shook these things pretty hard. Remember, when a machine is gyroscopically stabilized, you can shake it, but it's not going anywhere. It's like a gyroscope. It comes right back. No, I don't want to do that on purpose. But.
Do we have any other questions or comments?
What's the longest lifetime we currently have on operating centrifuge?
The longest lifetime we currently have on an operating centrifuge was demonstrated in the 82 to 85 program. We have, say, 25,000 machine years or thereabouts. How that would impute to a single machine lifetime, Bert, it's in the years, but no longer than that. We haven't demonstrated 15 years. We're designed for 30-year life. We don't have any wear parts in the machine. There are no wear parts.
You have fatigue.
Pardon?
You have fatigue as it goes.
Once you're up to speed, you don't. If you're going to start telling me about creep here in a minute, now we'll talk about that.
Everything has fatigue. I think that's his point.
We don't stress them very hard once we're up to speed. You stress your centrifuge getting up to speed, not when it's at speed.
The other question I've got is I conjecture the finance implications of what you're doing. Your next increment is what's really going to be the crux of whether you're going to be successful.
Yeah,
that's the crucial element if you're successful.
Well, it's a serial thing, Bert. If you can't make the single machine operate to your parameters, you can't make the cascade operate to your parameters. So you got to do the single machine, prove that it operates, that it does what it's supposed to do. Then you put it in cascade, prove that. Then you go for the money for the commercial plan. You can't get it without those two steps.
You'll have a commercial plan operating, and then it'll have some kind of financial basis.
Yes, sir.
And there'll be a demand for the product and competitive responses to where you are.
That's right.
Now, the real crux will be, I'm sure you've already tested the water, but what will be the need from the financing community to be able to get that next increment financed in terms of how long of a contract will the customer have to commit to in order to give you enough basis to get you financing?
We think it's like you've been sitting in our meetings almost with that question. We think we'll have up to 10-year contracts with options for longer.
Even with the speculated reaction from your competitors of trying to eat your lunch?
Nah. That competition is greatly overstated. They're both needed.
I have a related question. When does USCC expect to, or are they maybe already making a profit because of the 1/3 of the world business they have? Is that?
Yeah, we're making profit.
This is a big investment that's going to take a long time before.
Let me go back to my little 3-part chart, wherever that was. This, no, let's see. I have to find it. This part right here, Lee, this red part and this blue part, that's $150 million out of our internally generated cash flow. That's our investors' money that we're not paying out we pay a dividend, but we're making this investment out of our own business. We have another business that I haven't mentioned that's important to know about, and that is that we take Russian warheads and turn them into reactor fuel. It's called the Megatons to Megawatts program. We've so far destroyed 9,000 Russian warheads, some of which used to be pointed at Oak Ridge. We know that for sure.
Okay.
And popped.
Okay. I think we've had a very good question and answer session today. I forgot, I was remiss in not welcoming everyone back from the holiday break. I hope everyone had a good holidays and you didn't eat too much and only gained a minimal amount of weight. Unfortunately, I gained a little bit, so I'm on a program now to try to lose some weight. So thanks for coming. There are a lot of new people in the audience here that do not know that we have refreshments downstairs, and Ron will be down there to answer more questions. And so you're all invited for refreshments. But before we adjourn, let's express our appreciation again to Ron Green.
It's good to come home every now and then. Wish I could do it more often. Okay.
want people to know their interests and the facilities that are